what we're going to be going over here are Lagrange multipliers, and we're going to tie them into the directional derivatives. Now, this is where we're going to be looking at gradient calculations and also some visual perspective here when we include the Lagrange multiplier and the directional derivative. And we'll do it in terms of a production function, which is similar to the Cobb-Douglas production function. So what we're going to be doing here is we're going to try to maximize some profit here subject to some spending or cost constraint. And the reason we add in this Lagrange multiplier here, this Greek symbol I'm showing here, that is, we do it to include the cost constraint. So we're going to end up with 3 equations here and 3 variables here because we're dealing with a multivariate calculus type problem. Okay, so the first thing we have to do here, we have to set up our Lagrangian equation here. So this is going to be our Cobb-Douglas function or our production function here. We're going to have some revenue output here. That's our objective function here, and it's going to be subject to some cost or budget constraints. So our revenue output here, we're going to have, in this case, Q here represents our output or our profit in this case here, and it's time, and that's equal to 1400 here is the unit price that we receive here on the product we're selling, and we take that times some material and some labor raised to some exponential amounts here, and then we subtract from it the cost or the budget constraint. In this case, we're subtracting. In this case, we have a unit cost here on material of 350 and 200 here for labor, and it's subject to $40,000. We only can spend $40,000 on our material and labor. Okay, so to set up our Lagrangian equation, we just take our revenue output here, just bring that down here, and we would subtract from it our cost or our budget constraint here. This is where we add in that Lagrangian multiplier here, and you take that Lagrangian multiplier times the quantity here, 350 material plus 200 in labor minus 40,000 here, our amount that we're budgeted for. Okay, so that's the first thing we have to do to set up the Lagrangian. Now, the next thing here you have to, remember this was our output, our revenue here, and this was our cost constraint over here, and this is where we added in that Lagrangian multiplier. So next thing here, second thing, you find a gradient, and that's really taking the partial derivative of this Lagrangian function or this vector that we're looking at here. So you might want to do this with some software here. I've done it with MapleSoft here. So for our material here, we have the partial derivative with respect to our revenue here for our material here, and then we subtract from it our labor and our, our material unit, the price here on material times the Lagrangian. Then, okay, that's for our material here, and then for our labor here, what do? We add to it, take the partial derivative here of our revenue here in terms of our labor here, and then we'd be subtracting from it our cost here, and unit cost times for our labor times that Lagrangian again. So just remember, the computer or the software has done this for us, but just understand what's going on. And then we would add to it our cost here, the derivative here, partial derivative for the cost here, and you can see here you'd have a minus 350 for material, minus 200 here for times your labor here, plus 40,000. We just switch the signs around here, but essentially it's just that equation here with respect to the Lagrangian, the partial derivative here. So you don't see the Lagrangian in here when you've taken the partial derivative here. So you've got our material here, partial derivative here, material for our material, our labor, and we include our cost for the Lagrangian. So the third thing we have to do, we have to set up each partial derivative in equal to 0, and you didn't solve the set of equations. And this is really where your revenue and your cost, the slopes are equal. That's why we can set it up to 0. So we just take our partial derivatives here just bring them down here for material, set them equal to 0 here, and for our labor here, set it equal to 0. And remember, our Lagrangian is in there, multiplier is in there, and the same thing for your cost here. Okay, and just set everything equal to 0. So then put it into the software. The software will solve these 3 equations, 3 unknowns. See the unknowns here, you have labor, material, and the Lagrangian multiplier. And had we not included this Lagrangian multiplier, we would not have been able to solve the partial derivative when we're talking about sort of a multivariate calculus problem. So we have to put that Lagrangian in. So here's our solution. So many units of labor, 78.049, some fractional amount here. Material, 69.68. And then the Lagrangian multiplier, key number that we're going to have to look at here, 0.96608. And the key is here, in this case, our Lagrangian multiplier is less than 1. We really want to look at that Lagrangian, how much it's greater than 1 and how much it's less than 1. Okay, and then putting their solution here into our equation that we have for revenue and cost, you're going to get your minimum cost here at 40,000, which equals our cost constraint. We bumped up right against our cost constraint. And then revenue, we would have had 47,125. So the difference between our minimum cost, 40,000 here, revenue 47,125, gives us a profit here of 7,125. Okay, so now let's go and let's start with our visual perspective here. Okay, so moving up here, what I'm showing here is our production function, this blue figure here. I graphed that out here, plotted it out in 3D, the production function. And that included our cost. That was our cost plus our revenue here. That is our production function. And then these little red lines here, those are the isoquant or equal profit or equal quantity lines here, those red curves that go around on our production function here. And really I put a yellow, slice the yellow through here. That's really at ISO curve here at zero output here. That just to identify that we have a zero output here. And okay, and our cost constraint. The key is here, you see this sort of bluish green here. This is what we're bumping up that cost constraint, that 350 material plus 200 labor, up to $40,000. So that's the key here when we're talking about the Lagrangian and we'll look at the directional derivative here. And we're in our solution here, this red dot here, I bumped up right against our cost constraint. This cost constraint here is bluish green here, is slicing right through our production function at that term. And just remember our revenue portion I'm just showing here that we have here. Okay, and then the other thing we want to look at are these red line. Two things we want to look at. These red arrows here, plotted them out. Now, those red arrows here, quite a number of them, they're really the gradient field or our Q, our output. And that's really the direction. They give the direction and the magnitude of our greatest output in this case, and our greatest revenue in this case, or profit. And that's really what we're looking at. A whole bunch of these red arrows here, and they're pointing. It's kind of good to get a visual perspective here. A little hard to see them, but that's what's going on here. So, and then this other thing here, this red path that's following up here, where our output or our solution here falls right on that red path. That's our gradient path, and that's where you have the greatest increase. And you're really looking at some targeted point here when we're, in this case, when we're looking at, we'll look at a directional derivative. Okay, so that's for our first visual perspective here. And then let's go down over here. Okay, so let's put our equation in here. This is this revenue, and this little sign here is our gradient, and it's really the partial derivative here of both our revenue part of our function here. We take the partial derivative of that. That's that gradient. And that has to be equal to, the key is here, it's equal to the Lagrange multiplier here times our partial derivative here of our cost part of our function here. So we're taking the partial derivative, and that's really of both the revenue here and our cost here. They're equal only. They're different by a scalar or the Lagrangian multiplier here. The revenue here, partial derivative, or the gradient of our revenue here, and remember that's pointing in the greatest direction here, equals, again, a Lagrangian multiplier that we've calculated times the gradient here of our cost function. Okay, so going back to our little figure down here, again, I got that bluish green slice here. That's what we're bumping up against here. And I'm showing another thing here. These little this path here. I'm actually showing where we jumped over this our constraint here, and we're really not doing it. But we would really be concerned about jumping over it by reducing our costs and so forth. But anyway, it just shows the path that we're going at, and that's the path. It's just jumping above our gradient path here. We're not able to do it. We're bumping up against our cost constraint. But really what you're looking at, these gradients that we talk about, this little upside down figure here, this upside down delta figure, this is where our gradients here are perpendicular are parallel. The gradients are parallel. We're going to have our cost function, or our revenue function here, and our cost function here. Those two lines here, they're going in the direction here of our greatest increase. And these gradients are parallel. They're parallel to each other, plus they're perpendicular to the level curve at that point here. And that level curve would be our ISO curve, or our output, and that in this case would be our profit here at 7,125 here. So you see we're topping out here in based on our production function. There's no blue area really showing here. We're really maxing ourselves out here. Okay, so now and remember this red deal here is the path, but that's not the actual path that we're using. I'm just depicting it here. We would like to jump over that cost constraint maybe if we could reduce our cost here. Okay, so next we'll go in and we'll look at our calculations. Okay, before we get into our calculations, just looking at a visual perspective here, and I'm just looking at the side profile here of our production function. And this bluish green here, that's our constraint. That was at $40,000 maximum for material and labor that we can spend. And we're going to be tracing a gradient path here. That's the path here, the greatest output here. But I'm showing the gradient path here jumping over the cost constraint here. And I'm only showing that for a visual effect here. But you'd have to reduce your cost in order to do that. But in this case, we're going to be following it right along our production function here. Okay, so let's moving over here. Now let's get an idea what we're going to be looking at and look at our calculations. So what I'm showing here is this gradient path. It's these little round spheres going up here. And this is our solution. This big blue dot here or sphere is our solution that we came up with. And the key is here with the solution we have based on our constraint here, we're really maximizing our profit at this point. So you can see here when we start out with a very low inputs here, we have a very steep slope here. We're increasing our profit at a greater rate, and then we top it out here. We come up to a point here where we're going to top it out, and then after that point we're going to be going down here. That's following our change in slope or the gradient path here. So that's the key here. We'll be reducing our really profits or based on our equation here. And just looking at that Lagrangian multiplier here, this lambda, that equals we calculated that to be 0.96608 here. That was the multiplier. What it's really saying here is a dollar input to our production function, I'm showing here revenue and cost, is only giving us approximately 97 cents in output here. So we're really not gaining anything. We're losing about 3 cents on each dollar that we input just by trying to increase our production based on our production equation. And the other thing we're going to find out is this directional derivative here at this particular point here. Now that's the change in the unit output or the slope. It's also negative, and that correlates here with our Lagrangian multiplier because we're not getting as much out as we want, and our directional derivative we're going to calculate to be negative. Okay, so visually that's what we're going to be looking at. And then if we move up over here, this is where we got our gradient vectors here. These yellow ones would be our material and our labor here. And then these red vectors here, or arrows here, those are going to really be our directional derivative or our gradients here. And we're going to break those down between our cost gradient here, or directional derivative here, and our revenue directional derivative here, and make a comparison based on that Lagrangian multiplier that we have here. Okay, so going up and looking at our calculations. So first off, the gradient here, that's really taking those partial derivatives, which we've already done. We came up with our solution in these quantities here for material, labor, and our Lagrange multiplier. So just looking at our cost function here, this is where we had that Lagrange times 350 here. X I'm showing as material plus 200 here at times Y, which is our labor. So taking our partial here and this is really just determining the slope here when you take the partial derivative here of the cost function for M or our material here, 350 times lambda here. Again, the computer software has done this for me here. And then for our labor, taking a partial here in terms of our labor or FY here, you're going to 200 times lambda. And that's really just looking at the unit cost here for material and labor for each one of those here. So that's the slope here that we have for our labor, 200 times lambda. So our gradient here is just taking our X or our material slope here, 350 times lambda, plus our labor slope here, or 200 times lambda. But this is where the multiplier comes into effect to get the gradient. So all you're going to do is substitute in here 0.96608 here in lambda for your material here, and same for your labor, and you're going to get the gradient here after applying your Lagrange multiplier here is 338.13 here for material, plus 193.22 here for labor. Okay, so that's what we're going to deal with here for our cost. Now for our revenue, that's just that 1400 here times your exponential amounts for material and labor here raised to those amounts. So for the partial derivative in terms of m here, you're going to get this amount here, and that's going to give you, substituting in the in our solution numbers here, we're going to get a slope of 338.12. That's for material here. Remember, that's for our greatest output. And then for the partial here in terms of our labor here, we're going to have this quantity here, and substituting in our material and labor from our solution, we're going to get a slope here of 193.21. So the key is here for our x slope, our gradient here for our material, 338.12, plus for our material at y slope here for material, or labor, excuse me, at 193.21 here. Now, the key is here, these gradients here, you can see here for our revenue here equals our gradient here for our labor here, so excuse me, our cost here. So that's the key point we're looking at, and that is the key here with the gradients. We're looking at our greatest output. At our solution amounts, our gradients are equal between the two. Okay, so that's for our gradient here. Now let's go and let's look at our partial derivative, or excuse me, our directional derivative here, and that's really the change in unit output or the slope at those points. So what we've done here, first off, let's just show it here. These are at the point, or our solution points here that I'm showing here for labor, material, and our Lagrangian multiplier that we solve for. And really all we did is this is just showing the partial derivative of that Lagrangian function that we have here for material here. You get the material for the revenue portion here, and then the computer said we had the derivative is subtracting out your unit cost here for material, and then for labor here, then you add to it for the labor vector, essentially, as we're looking at for your labor, your partial derivative, and then the unit cost here for labor. And that's taking the partial derivative when we look at that Lagrangian equation. That included our Lagrangian here. Okay, so substituting in our solution into our partial derivative here, you're going to come up with your gradient at, for the first one, minus 11.88 plus minus 6.79 here. By that substitution, subtracting out your unit labor cost here and your unit material cost here. Now, the other thing is, we can't just stop here. We got to include our unit vector here. And we're not getting into all the calculations, but it's just taking a right triangle here. You got your material amount, your labor amount, you square those, take the square root of it, and divide them by what your material and labor, and you're going to come up with the unit vector here. This is just simple math that you're looking at. So for unit vector for material, it's going to be 0.6660483. We have to put everything in terms of that unit vector here, and that's for material, plus you're going to have 0.74 and so on here for your labor. And then you just take those times the gradient that you have here, and this is what you're going to come up with. The actual amount, just adding those together, you're going to get that negative 12 minus 12.977. And it's really taking your revenue less your cost here. So you can see your cost here is greater than your revenue when we talked about our gradient here. So that's why we're headed down in a negative direction here in our directional derivative. Our unit output per slope is actually unit output, or at that slope, is actually decreasing. So now, the same thing for our cost here. Remember our gradient here, 350 for material, 200 here for labor. Take your unit vector times that. You're going to come up with, that we have here, the unit vector here for your material times 350, just to understand that, and then the unit vector here for your labor here, that one, times 200. So you're adding those two together, your directional derivative is 382.29. That's for our cost here. And then same thing for our revenue. Just remember our gradient, we calculated that, 338 plus 193 here. Take that times your unit vector here, and you're going to come up with the directional derivative at 369.9 0.31. So you can see here our directional derivative here, that a gradient vector that we're looking at here for our cost is greater than our revenue by exactly the amount here, 12.977 here. It's going down in a negative direction. So you want to be looking at that directional derivative to see what you're adding when you increase your production here in terms of material and labor here. Okay, so those are for our calculations. Then if we went over here, let's look at it. So remember we took that our Lagrangian here times the gradient here of our material and labor, and then we had that $40,000 cost constraint. So what we're talking about for our material, or for our cost vector here, remember we had 200 here for our labor on a unit basis and 350 here for material, and those are those yellow vectors or arrows that we're looking at here. And then that directional derivative based on what we had calculated here is $382 dollar amount here. And that's for our cost here. And if we gone down to our revenue, same thing. We just take that revenue portion here, the gradient of that. And in this case, our directional derivative, or our gradient that we calculate here, would be 193 for our labor, 338 for our material here. And let's look at that. Let's go back to this one, because it was easy enough to do the one up here for labor and material, because those are just the unit amounts here. But if we go back here, just to understand what we're looking at, maybe we could look at it in both cases. So remember that gradient we have here for our cost here, and we got up directional derivative, we come up here 382. If we went over here, let's look at it. See, there is where it is here. That's our directional derivative here based on the factor that we had to factor in that unit vector here. And the same for our revenue portion here. We come up with 338, 193. You can see it here. 338, 193. And then our revenue, or our directional derivative, 369. Shown here, directional derivative. So the revenue here, just to understand it pictorially here, if we take now our cost, our directional derivative on our cost here was 382, so we have to subtract our cost from our revenue here, 369. So this is where you come in. That difference gives us a negative directional derivative here of 13 here. Okay, so that's how we're looking at it pictorially here. Looking at it in vectors between our gradient vectors for labor, material here, and our directional derivative. And then if we went up here, let's go and look at it. So this is really what's going on. Remember that solution point here based on our constraint here. We had a constraint here, and this was our production function shown here in blue. So our revenue was going out in this direction here at 369 here, but our cost is actually going in the would be going in the opposite direction here at 382. So ultimately our directional derivative, our unit output, our change in output at our solution point here is actually negative here by the difference between those two, approximately $13 here. Okay, so that's what we're talking about. And if we go back down here, let's just go back down here one more time. Okay, so looking at our gradient path here, these little circle, or these spheres here, that's our directional path here, the greatest increase. And we got to blue here. Remember that blue here, that was really those matching those vectors up here for our material and labor here. So we got here, and then there's our direction, or here's our plane for our material and labor vectors and our directional derivative. But you see, this is where we maxed it out. We got right to the top here, and now we're headed down a slippery slope here into lose more output. If we, again, this is the case here with our Lagrangian multiplier here, 0.966 here. You take that times $1 input into, spend $1 more here for material and labor, and all you're going to get out is 97 cents here, or 3 cents less. So you're losing money here. Well, you're making a profit up to a certain point here, but your revenues are going down after you meet that point. And that's goes in with our directional derivative, ties in with our directional derivative here at minus $13 or for unit output. So unit in, this is direct. We're actually going down at $13 here based on our directional derivative, or the change in the unit output or the slope. Okay, so that's pretty much going to summarize it. Just remember, you have to use this Lagrangian, substitute it in, or put it into your equation so you can solve these multivariate calculus type equations that we were looking at here, m raised to some power, l raised to some power, and then based on the constraint. We had to add that Lagrangian in here to include our constraints here. Otherwise, we couldn't have come up with a solution here. Okay, so that'll summarize our discussion.